When analyzing circuits, there's two rules that become our most basic tool, and those are the Kirchhoff rules, the junction rule or node rule and the loop rule. And we've seen them both before. One is that the junction rule is if you have a junction, these are all wires, and this is some junction where they're all soldered together, and I have some current flowing in, some current flowing out, some current flowing out, some current flowing in. Call this I1, I2, I3, I4. Okay, so I have all of those currents flowing in and out of this junction. What the junction rule says is that what goes in must come out. Okay. Sometimes we'll put summation signs here, meaning all of the inputs added together must equal all of the outputs added together. So in this case, I have I1 as an input, I have I2 as an input, and then that's all of my inputs, and I have I3 and I4 as outputs in this case. And this is an equation that relates our variables. And so if I have something like this, okay, and I know maybe there's 2 amps of current flowing in from this side, and there's 1 amp of current flowing out that end, but I don't know what this current is here. Well, I can now find it. Even though, looking at the numbers, I can see that this must be an output. But even if I didn't know, it was too complicated and couldn't see that right off the bat, I could just follow this rule. And I say, okay, this is obviously an input. This is obviously an output. I don't know what this is, so I'm just going to put it on the output. Okay. And so I have, I'll call this I1, I2, and I'll call this I3. So I have I1 as an input, okay, and I'm choosing it to be the only input. And then I have I2, which is definitely an output. And then I3, I'm going to just assume it's an output, so plus I3. And I could be wrong, I could be wrong, but it's okay. I'll show you how to correct that. So if I solve for I3 now, I get I1 minus I2, which is 2 minus 1, which is 1, and I got a 1, a positive 1, which means I was correct in my guess. It was an output. Now, had I thought maybe it's an input, I could have put I1 plus I3 equals I2. Solving for I3, I get I2 minus I1, which is 1 minus 2, which is negative 1. Which means, I got a negative sign. The negative sign means I put it on the wrong side of the equation. It really is an output. Okay, so I assumed it was an input. I got a negative sign, which means it's actually going out. So just like other things where sign just means a direction, same thing here is when we're making an algebraic guess of is it an input or an output, and I get a minus sign, it just means you made the wrong guess, which is fine. We have the tools to solve for that. So that's the Kirchhoff rules. Okay. Now the loop rules we've seen before too. It's basically when I start at a place and I go somewhere and get back to that place. Well, the potential change along every segment of this, all the way around from here to here, plus here to here, plus here to here, plus here to here, so on all the way around. If I were to find the delta V's between all of these points, it must all add up to 0. And I say delta V loop equals 0. And so when you have a circuit, a complete circuit that's got a full loop, I can have, let's say I have a battery here and a resistor here and another resistor here, bring it back, and maybe I have another resistor here, bring it back. And this delta V battery, R1, R2, R3, okay. I can apply this to every loop I see. Now here, there are actually 3 different loops. There's this loop, okay. There's this loop, and there's the whole loop, going all the way around this outside. So there are 3 different loops. Now, only 2 of those loops are independent, meaning when I try and apply this as an equation to 2 of those loops, I could add those two equations together and get the third loop. And so this only gives me less than, there's a total number of loops, but the number of equations, independent equations I can get from it are less than that. It just depends on the type of loops and how they're combined. Okay. And so we can apply that. So for example, if I were to apply it to this one, I could say starting maybe right here and going around this loop, all right, I'm going to say that I've got delta V battery, and I gain across this battery because I'm going from the negative to the positive side, and I'm going to go across this resistor. Now, we'll talk about potential across the resistor in a second, but basically I'm going to have plus delta V R1, and then I come over to here and I get delta V R2, and I get back to that spot, and I'm back to where I began, therefore that whole thing must equal 0. Now notice at the junctions, I didn't really care that there were junctions. The junction rule cares about junctions. The loop rule just cares about loops. And so I would be able to apply a junction rule to the currents right here as well as right here. And so I can apply this and this to analyze this circuit. So recognize that the node or junction rule and the loop rule are both tools to analyze circuits. Okay, now before leaving this, let's go ahead and talk one thing. How do you find the potential difference across the resistor? Well, that's through Ohm's law. We have delta V equals IR. Okay. So if I want to find the potential across the resistor, I need to know the current flowing through it. Okay. And based on all the knowns, I can use all my tools to try and find that. But what we'll focus on here is that when I go around a loop in my loop rule, I assume a direction of current. So since I went clockwise around this loop, I'm just pretending or assuming that the current's going to flow this way. Kind of makes sense because my positive side of my battery is here, and we know that a traditional current is driven from negative to positive. So that seems like a good assumption. I'm probably correct. But it doesn't matter. Just like over here, if I was wrong, I just get a minus sign. But with that assumption, it means across this resistor, the current is flowing to the right in the direction, and I am going in the direction of that current, which means that I am going downhill across the resistor because resistors decrease potential. So in this case, I would have a delta VB minus IR1. Okay. And I'm going to have to be a little bit more careful. I'm going to call that I1 because when I get to this resistor, I'm assuming the current's flowing this way. Call it I2. And so I'm crossing that one. And so that's also negative. I'm going in the direction of the current, and therefore I've got negative I2 R2 equals 0. Okay. Now, honestly, I could have chosen this current to point upward. It's all based on your choice, and just chosen to go this direction. And therefore this would have been a loss of voltage, and this would have been a gain. And with my other knowledge of my equations, I could have solved for these, and I would have gotten one of these to be a negative current, which means I just picked the wrong sign. And that's fine. That's fine if you do it. For example, let's look at this one. We've already chosen this one to be down, which means I'm fixed. I can't, when I'm doing this loop over here, I can't change that because I've already chosen that to be down. Okay. Now I'm going to go ahead and choose this one to be down. Okay, I'll call that I3. And so if I do this loop now, let's say I'll start right here. I'm going this way around the loop. I'm going to start right here. And so I'm going opposite the current. Now, if current goes towards lower potential across the resistor, that means I'm gaining potential. That one I'm going to get a plus I2R2 because I went opposite it. And now I'm going in the direction of current, so it's minus I3R3, and I get back to where I started, and I get 0. So our two rules for analyzing circuits, and then how to find how to designate directions of current, and then directions of path, and then whether or not the potential will be positive or negative based on the current direction and how I go across that current. If I go in the direction of the current or if I go opposite the direction of the current.